This is problem number 7 on the sample test problems for test number 2. Suppose that the number of bacteria in milk grows at a rate of 10% per day once the milk has been bottled. When the milk is put in the bottles, it has an average bacteria count of 500 million bacteria per bottle. Let P equal F of T be the number of bacteria in millions present T days after the milk is bottled. A, write a formula for P of the form F of T equals P0A to the T. Okay, first thing we need to know is that P0 is the initial amount. And in this case, the initial amount is 500 million, but we're doing this problem in millions, so P0 is just 500. And in order to find A, all we have to use is a nifty little formula, and that's that A is 1 plus R, where R is the growth rate. And so in this case, R is 10%, or 0.10. And so we'll bring that back down here, 1 plus 0.10. So the A we want is 1.10. So mushing these two things together, we finally get our formula. F of T equals 500 times 1.10 to the T. Part B, write a formula for P of the form F of T equals P0e to the KT. All right, given that we're looking for K here, K is called the continuous growth rate, and we don't have it in this problem. So what I'm going to do is use the answer to the previous question to answer this one. So we'll start with the same P0. P0 is still 500. It's the same initial amount. And here's what we know. We know that e to the kt is supposed to agree with a to the t. Those two pieces are exactly in the same spots, and we need them to equal each other. Take the tth root of both sides, or raise both sides to the 1 over t, and the t's cancel, so we just get e to the k is a. But we happen to know what a is. We found it up above. E to the k is 1.10. The goal is to find k. So what should we do to both sides? We'll hit both sides with the natural log. And on the left-hand side, we just get k. That's why we hit it with an ln. So k is ln of 1.10. And we'll go ahead and get a decimal from the calculator. As a quick check, you might be able to estimate this number before you type it in. We know that the growth rate is 10% per day. So to get that same effect, if we're thinking of that growth as being continuous at every moment of the day, do we expect the answer here for k to be a little more or a little less than 10%? So pause it if you want to right here just to think about that question. And once we've thought about it, hopefully we see that the k we're going to get is going to be a little less than that 10%, because by compounding the growth continuously, some number a little smaller than 10% actually has an effect that's a little bigger than itself. It's going to build up to that 10%. So that said, let's type it into the calculator. We're just looking for ln of 1.10. And we get a number just under 10%. 0.09531. So that means our final answer is f of t equals P0 is still 500. It's no longer a to the t, it's now e to the kt. Part C, what is the doubling time for the bacteria in bottled milk? You can use either formula that we have in black. I'm going to use the top one, 500 times 1.10 to the t. So we know f of t is 500 times 1.10 to the t, and we want to know how long it takes to double. So the goal is to find t, but in this case we actually know what f of t is. If we're going to double and we start with 500, and we just need to wait to get to 1,000. Divide both sides by 500, and we get 2 equals 1.10 to the t. Again, solving for t, so hit both sides with an ln. And here's one of these nice properties. Let me actually put that t inside just so it's really clear. So here's one of the nice properties of ln is that if you have ln of some number to a power, that power gets to move right down in front. So this says ln of 2 is t ln of 1.10. So that t is right there in the front. And then finally, to solve for t, we divide both sides by ln of 1.10. And actually, some of you maybe have seen this formula before, but the doubling time turns out is always equal to ln of 2 divided by ln of a. And that's what we saw by going through this calculation. So let's go ahead and find the doubling time on the calculator. There is something called the rule of 72 that can help you estimate doubling time without the calculator. Basically, it says take 72 and divide it by r, and actually leave r as the percent. So don't make it 0.10, but leave r as 10. And if you take 72 and divide it by 10, you get 7.2, which is going to be close to the doubling time we're about to get. So our estimate is about 7.2 days by taking 72 and dividing it by 10%. So let's see how close that is on the calculator. So we're doing ln of 2 divided by ln of 1.10. Something near 7.2 days. That's pretty close. So about 7.27. B. Suppose milk cannot be safely consumed if the bacteria count is greater than 3 billion per bottle. How many days will the milk to be safe to drink once it has been bottled? Solve this algebraically. Okay, first thing we need to do is convert that 3 billion. Everything we've been doing with this function has been in millions. So the question is 3 billion is equal to how many million? And the answer is 3,000. So what we'll do here is use one of our two formulas, either part A or part B. I'm going to use the part A answer again. We know the amount of bacteria is 500 times 1.10 to the t. And I want to know how long does it take for the bacteria to grow to this 3,000 million. Solving this is going to be quite similar to how we solved the equation up above. So divide both sides by 500. Hit both sides with an ln. We'll go ahead and bring the t down in the front just to save a step, but it's the same property we just saw up above. And then finally, t is ln of 6 divided by ln of 1.10. Okay, so we'll type that into the calculator. Again, you probably could estimate this number. We've already figured out it takes about 7 days for the amount of bacteria to double. So we just have to calculate how many doubles would it take to go from 500 to 3,000. So one doubling will get us to 1,000. Double again to get to 2,000. Double a third time gets you to 4,000. So I'm looking for something between 2 and 3 doubles. And every double is about 7 days. So 2 doubles is 14 days, and 3 doubles is 21 days. So looking for something in between 14 and 21 when we type this thing in. So let's see how close that is. ln of 6 divided by ln of 1.010. And again, something between 14 and 21. So that answer is reasonable, about 18.8 days. Part E, write a formula for the inverse function P inverse. What does it measure? Okay, so finding the inverse is just a process. First, we have to pick which formula we're going to use. I'm going to keep using this 500 times 1.10 to the t. Now, the first step for finding the inverse of a certain function is sometimes to swap the two variables. So you'd swap the t and the p, and then you'd solve for p in its new position. I'm actually not going to do that in this case. I'm going to just solve for the t where it currently is. So the goal is to solve for t. So the first step is to divide both sides by 500. And again, solving for t, that variable is in the exponent. So we'll hit both sides with an ln. And I'll go ahead and bring the t down, again saving a step. And then finally solving for t, we get ln of p over 500 divided by ln of 1.10. So that's the formula. Maybe it doesn't necessarily look like an inverse because we haven't written it in the standard inverse function notation way. So maybe I'll do that here. I'll say that f inverse of p, because it sure feels like p is the input now, is equal to, and then we'll copy all of this. So that's our inverse function. And the reason that I didn't want to swap the t and the p is that I think leaving them as they are gives you a real good head start into figuring out what the inverse function actually measures. So in this case, the input is p, population, number of bacteria, and the output is t, which is measuring time in days. So input a certain population, and this function outputs the time it takes to get to that population, and that's our explanation of what it measures. Given a population of bacteria, meaning how many bacteria are there, f inverse of p outputs how many days it takes to achieve that population. Your explanation of what f inverse measures doesn't have to be word for word with that, but it does need to get the idea that you're inputting a certain population, and this function will tell you how long it takes to get there.